In this part, we want to work on background idea cyclic additions. We want to solve this last problem of AMC 12 2021 fall, and also BMO round 2, British Mathematical Olympiad. Now round 2 is similar, we can say, to USAMO. The difficulty, and again this problem can be solved with same idea, and also it is a problem from a book. I can say the book is for around 20 years ago. By solving this problem, I will show you the idea is what. Then we try to solve this AMC problem and this BMO problem. I solved this BMO problem before in my other videos. You can check that. So I will solve this problem. I will leave this one as homework. And we will solve this AMC problem. Okay, and if you had any question about this idea or you want to learn other ideas, as I said before, feel free to send message to my WhatsApp number in the description and comments. Let's solve this problem. A is from 1 to 100. Number of elements in A equal to 11. Sorry, is 11. A is A1 to A11. 5 divides A1, sum of the elements in A. How many A satisfy these conditions? Okay. So, I say an arbitrary, for example, subset A, for example, 1, 2, 3, 5, 6, 7, 8, 9, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 13, 15, or 13, 16. It is an arbitrary A that it doesn't satisfy this condition necessarily. But I define what? I say, okay, it is A0. A1 is what? Cyclic addition means what? I add each element 1 to each element. It will be 2, it will be 3, it will be 4. I add 1 to each element. So it will be 6, 7, 8, 9, 10, 12, 14, 17. Then I define A2 is 2 plus each elements here. It will be what? It will be 3, it will be 4, or 1 plus elements here. 4, 5, 7, 8, 9, 10, 11, 13, 15, 18. And then I continue. And I know because our elements are in main universal set is 1 to 100. If we reach 100 in next part, it will be 1 again. That's the reason I say cyclic, like mods. So 100. So after 1 we see 2, after 2 we see 3, after that we see 100, after 99, and after 100 we will see 1. So, for example, if you want to consider A99, it will be 99 plus 1, it is 100. 99 plus 2, 101, so it will be 1. 102, it is 2. 99 plus this 104, then 5, then 6, then 7, then 8. 99 plus 9, 108, it will be 8. 99 plus this will be 10. Then it will be 12. Then it will be 15. Okay? And if I write a 100, it will be what? 1, 2, 3, 5, 6, 7, 8, 9, 11, 13, 16. So we will see A100 will be same as A0. Okay? So we've considered what? We considered a subset A0 with 11 elements, then A1, A2, to A99. So we have 100 subsets here. Okay? Then we select another, for example, subset B0, B1, that is not here, B2, to B99. And we know that these two cycles don't have any intersection, because if one element, for example, A99 equal to this, for example, B99 equal to this one, so if it will be plus 1, A2 will be B0, then the two cycles are exactly the same. So we have some these things. Now we work on, in each cycle, we want to see how many of elements, how many of subsets have a sum multiple of what? 5. So suppose, for example, this sum is S. We add all elements by 1. Okay, so it will be S plus 11. And let me tell you, we want to constant mod 5. So if 100 goes to 1, again, if you constant mod 5, it will be add by 1 because 100 mod 5 is 0. So we will see in all cases, we can say all elements will be add by 1. And if you constant mod 5, it will be again S plus 1. So it will be S plus 1, S plus 2 mod 5. And can we continue? S plus 99. Okay. Now, if we consider sum mod 5 for each part, A0 to A99, we have S plus 1, S plus 2, S plus 3, S plus 4, S plus 5. And so, in each 5 consecutive number, we know we can see all remainders when divided by 5. So, exactly one of them is multiple of 5. Again, from S plus 5 to S plus 9, we have exactly one good number here, one good number up to S plus what? S plus 99. And here is S plus 95. Again, one good number. So there are 100 numbers. If you divide by 5, we have 20 good numbers. Okay, in each cycle, so we have 20 good numbers, 20 good numbers, and so on. So the answer will be what? How many subsets with 11 elements are there? 100, choose 11. Now, how many cycles are there? You divide it by 100 and its number of cycles. Each cycle has how many good elements or good subsets? 20. So you should multiply by 20. Each cycle has 20 good members. So number of cycles times 20 is the answer. And if you simplify, it will be 111 over 5. So 1/5 of them are good. Okay, so it was the idea cyclic addition. And if you don't know the idea and want to solve for some of these types of problem, they will be so much hard. So you can do this problem as homework, this BMO round 2 2019. Let's focus on this AMC 12A problem. Okay, again, when we want to solve this problem, we try to use small example. Okay, that's one of the most important idea in AMC, AME, USAMO, IMO. And I solved IMO problems 1 and 4, two of them, IMO 2023, and I've used small example in both of them. Here, it says let m is at least 5 be an odd integer, and let dm denote the number of quadruples a1, a2, a3, a4 of distinct integers with ai from 1 to m for all I such that m divides a1 plus a2 plus a3 plus a4. There is a polynomial q of x equal to c3x cubed plus c2x squared plus c1x plus c0 such that dm equal to qm for all odd integers m greater than or equal to 5. What is c1? So when we want to solve this problem, we will see that understanding this problem is also hard. So sometimes a small example also helps us to understand the problem. So here, the smallest case that I can check is m equal to what? M equal to 5. And dm denote the number of quadruples is okay. So ai, we have what? We have a1 to a4, and ai are from 1 to m, which is 1 to 5. And we know that m divides, or 5 here divides a1 plus a2 plus a3 plus a4. And a1 to a4 should be distinct numbers, different. So what are the numbers 1, 2, 3, 4, 5? So I should remove one of them, and then a1, a2, a3, a4 will be that. So you should remove one of them such that the sum be multiple of 5. If you consider 1 plus 2, all of them, 3 plus 4, before removing one number, it will be what? 5 times 6 over 2 which will be 15, because 1 to n is n times n plus 1 over 2. There are around 5, 6 identities you should memorize if you want to learn them. Hockey stick identity, Vandermonde's identity, triangular form if you want to learn them. As I said before, feel free to send message to my WhatsApp number in the description and comments. Because it is 15, if I remove 1, it is bad. Because then some of the others will be 14. It should be multiple of 5. So because it is multiple of 5, you should remove 1 multiple of 5. So A1, A2, A3, A4 should be 1, 2, 3, 4, and permutation of that. Now, here, I want to say something for this part. But because it is so much obvious, so the answer is what? Let's calculate the answer. D5 is what? All permutations of 1 to 4, 4 factorial, which is 24. Let's focus on 7. M7, AIs are from 1 to 7. We know M or 7 divides A1 plus A2 plus A3 plus A4. And, okay, AIs are 1, 2, 3, 4, 5, 6, 7. Okay. Now, here, for example, let's find a good case. Some of them should be multiple of 7. So, for example, 7 or 6, 1, 2, 5 is good. For example, look, 1 plus 2 plus 5 plus 6. Some of them is 14, it is good. And we can consider all permutations. Okay? We can try to find all others. Now I want to say what? I say, okay, suppose we have 1, 2, 5, 6. I want to use cyclic addition here. So it will be 2, 3, 6, 7. The next one will be 3, 4, 7. 7 plus 1, we don't have 8, it will be 1 again. So let's consider this cyclic addition. 4, 5, 1, 2. 5, 6, 2, 3. 6, 7, 3, 4. If we add 1, 7, 1, 4, 5. And 1, 2, 5, 6. Okay, if we consider it goes, this one is the first one. It goes to this one, 2, 3, 4, 5, 6, 7. So we've created a cycle. And how many of them are good in this cycle? The sum here is what? Now we consider the sum mod 7. The sum here is what, for example, S. Here is 0. Then I add all of them by 1. So it will be S plus 4. Okay? Then let's consider something. Here, 7 goes to 1. For example, when 4 goes to 5, we know it's plus 1. When 7 goes to 1, if we consider mod 7, it will be what? Minus 6. What we want to see mod 7 is what? Again, it is plus 1 because you can add 7. So we will see in all cases, if we consider mod 7, each element will be added by 1. So if we consider mod 7, it will be S plus 4 times 2. Here, let's write S plus 4 times 3. And the last part is S plus 4 times 1, 2, 3, 4, 5, 6. Now I want to prove all elements, all the sums here. We have 7 members on this cycle. I want to say a sum of all of them are different. Suppose S plus 4i is congruent to S plus 4j mod 7. So we subtract S from both sides. So 4i is congruent to 4j mod 7. Then I divide both sides by 4. So I is congruent to j mod 7 over GCD of 4 and 7. Okay, GCD of 4 and 7, it is a rule in modular. If you don't know that, or if you want to learn more things about number theory, as I said before, feel free to send message to my WhatsApp number in the description and comment. So I is congruent to J mod GCD of 4 and 7 is 1, so it's mod 7. And because I and J here, as you can see, 4 times 1, 4 times 2 to 4 times 6. I and j are from 0, because it starts from s, I0, to 6. So when the remainder, when divided by 7 equals, so I equal to j. And we understand all members here, if we consider members here, the remainder when divided by 7 are different. And how many members are there? 7 members. So, because we have 7 members and all remainders are different, we have one of them 0, one of them 1, one of them 2, and mod, we consider mod 7, one of them 3, one of them 4, one of them 5, 6, mod 7. So we have all remainders once. Okay? So now let's consider this cyclic addition, and we want to solve problem for 7. So 1 to 7. How many cases are there? A1, A2, A3, A4, AI are from 1 to 7. So A1 has 7 cases, they are distinct. A2 has 6 cases. A3. And when we add all of them by 1, they will be still distinct because we add all of them by 1. So it is 5. A4 is 4. So we have these number of, let's consider these things, for example, elements or vertex. For each quadruple, we consider vertex. So we have this. Now, we know that we can, each of them is in one cycle. 1, 2, 3, 4, 5, 6, 7. Okay? And we know in each cycle, only one of them is good. So we divide by 7. So it will be our d of 7. Okay, we cancel this. So d of 7 is 6 times 5 times 4. Now we generalize this idea for general m. I say, okay, we know m is odd. We want that m divides a1 plus a2 plus a3 plus a4. We say, okay, if we consider one quadruple a1, a2, a3, a4, and add by 1, a1 plus 1, cyclic addition, a2 plus 1, a3 plus 1, a4 plus 1. If we consider this sum, for example, equal to s, or let's consider this sum equal to, for example, r, then this sum will be r plus 4. But we know when ai reaches m, for example, when ai is 1, it goes to 2. But when it is 2, it goes to 3, for example. But when it is in m, it goes to 1. So in all of them, we have plus 1. Here we have minus m minus 1. But if we consider mod m, because we want to consider divisibility mod m, negative m minus 1, if you add m, it will be 1. So in all cases, it will be add by 1. We are considering mod m. And it goes up to a1 plus m minus 1, a2 plus m minus 1, a3 plus m minus 1, a4 plus m minus 1. If you add m, it will be same. Okay, same as first one. So it was this one, this one, this one, and so on. And then it goes to first one. Okay. Now, we know we can consider again r plus 4 to r plus 4 times it is m minus 1. Now I want to say all sums are different mod m. Why? Because if I consider r plus 4i is congruent to r plus 4j mod m, then I can subtract r, 4i is congruent to 4j mod m. M is odd, so if we divide by 4, 4 and m are relatively prime. Mod m, because we know I and j are from 0 to m minus 1. Again, so we conclude I equal to j. Okay, so all these numbers have different remainders when divided by m. So one of them 0 because we have m numbers, 0, 1, 2 to m minus 1. So exactly one of them is good. So here, if I want to find dm equal to m, the number of quadruple, m minus 1, m minus 2. Okay, m minus 2, m minus 3. Now, we know how many cycles are there? These divided by m, because in each cycle we have m quadruples. So we divide this, And it will be m minus 1 times m minus 2 times m minus 3. Now the problem says what? The problem says dm equal to qm for all odd integers m. So we found dm is this, q of m, because the degree is 3 when it is equal for more than 3 values to dm, they are completely equal. So we consider q of x equal to d of x equal to d of x equal to x minus 1, x minus 2, x minus 3. And if we consider this x cubed plus, if we want to find x squared, we want only coefficient of x, but let's also calculate x squared. X minus 3, x minus 2, x minus 1. And if we consider coefficient of x here, then negative 2, negative 3 is 6, multiply. This x, negative 1, negative 3 plus 3. This x, negative 1, negative 2 plus 2. And constant terms, negative 1 times negative 2 times negative 3, negative 6. Okay? 6 plus 3, 9 plus 2, 11. Here also it will be negative 6. So it will be x cubed minus 6x squared plus 11x minus 6. It is equal to c3x cubed plus c2x squared plus c1x plus c0. The problem says c1 is what? c1 is 11. Okay? Okay, so the answer is choice. And here we solve this problem of AMC completely, and this, as I said, this exam is related to USAMO. So this idea can be used in, for example, qualifying level in AMC, like AMC, or also it can be useful in exams that are related to USAMO, IMO. So cyclic addition, the idea here we said, is so much useful. Cyclic addition's background idea of this part. If you want to learn other background ideas or want to solve more problems or want to prepare for AMC, BMO, any national exams, any math exams, or want to learn there are around 40, 50 important ideas in each topic, combinatorics, algebra, number theory, and geometry. If you want to learn them, as I said before, feel free to send message to my WhatsApp number in the description and comments. Thanks.